الآن يمكنكم المشاركة في مبادرة الأيام الرقمية تحت شعار انطلق بقوة مع جوجل، والتي يتناول فيها خبراء جوجل عناوين جديدة أسبوعيا مثل السحابيات، مهارات من جوجل، أندرويد، فلتر، ذكاء الآلة، فايربيس، ديزاين ثينكينج، مقسمة إلى دورات وورشات عمل يومية بالإضافة إلى مسابقات أسبوعية. شاهد الأيام الرقمية مباشرة على اليوتيوب وشارك رأيك وأسئلتك مع خبراء جوجل، واحصل على شهادة حضور في كل محاضرة تشترك فيها. هذا وأكثر من الأحد إلى الخميس ابتداء من الساعة 9 بتوقيت دبي عبر الرابط المبين youtube.com/gdgmena.
Hello everyone, Assalamu alaikum. I hope you're doing well and in the best of your health. So today, inshallah, we're gonna talk about the optimizers in deep learning. So we're gonna see the general idea behind optimizers and some common or the common used optimizers in deep learning. But before digging in our topic, let me introduce myself. I'm Leila Habib, GDGCD Bil'Abbas lead and WTM ambassador. Picking the right optimizers with the right parameters can help you squeeze the last bit of accuracy out of your neural network model. With that said, if you worked on deep learning model before, you already used a number of optimization algorithms to train this deep learning model, right? So they were the tool that allow us to continue updating models parameters and to minimize the value of the loss function as evaluated on the training set. Indeed, any one content with the training optimization is black box device. To minimize the objective function in a simple setting might well content on oneself with the knowledge that there exists an array in quantities such as the procedure. Okay, so with a name such as the stochastic gradient descent or ADAM. To do well, however, some deeper knowledge is required. Optimization algorithms are important for deep learning, and on one hand, training a complex deep learning model can take hours, days, or even weeks. The performance of the optimization algorithm directly affect the model's training efficiency. On the other hand, understanding the principle of different optimization algorithms and the role of their hyperparameters will enable us to tune hyperparameters in the targeted manner to improve the performance of deep learning model, if we can say. So to sum up all what the optimizers are algorithms or methods used to change the attribute of a neural network, such as weights and learning rates, in order to reduce the losses. So here is, let's say, what you expect to learn from this session or what you expect to see in this session. So here is the agenda. We're going to talk about the most common optimizers. As I said, we will see the gradient descent, stochastic gradient descent, mini-batch stochastic gradient descent, momentum, and the root mean square propagation, and ADA delta and ADA. Let's start with gradient descent. So in this section, we are going to understand the basic concept or underlying gradient descent, although it's rarely used directly in deep learning. An understanding of gradient descent is the key understanding of stochastic gradient descent algorithm. So for instance, the optimization problem might diverge due an overly large learning rate. This phenomenon can already be seen in gradient descent. Likewise, preconditioning, let's say, is a common technique in gradient descent and carries over to more advanced algorithm. Okay, so the gradient descent is the most basic, but most used optimization algorithm is used heavily in linear regression or let's say the classification problems. Okay, so let's start with this simple special case. Suppose we are located in this mountain here and without a map and do not know how to reach the bottom of this mountain. Okay, so we decide to take a step. This is So to go further in the direction to the steepest and the most easy to go down here. Okay. So the current position, and then continue to take small steps, steepest direction toward the next position. This step by step to reach here the bottom, go all the way to think that we have reached that bottom that we want to reach here in this mountain. Okay, so here the direction of the mountain through the steepest path is the gradient. Gradient descent is the first order optimization algorithm, also known as the steepest descent method. Okay, so to find this local minimum here of any function, use the gradient descent method. Iterative search must be performed to specified step distance point in this opposite direction of let's say of our current points. Okay, so or the approximate gradient if the search is reversed and in the opposite direction from this bottom position or this bottom side to up there here. So here we're talking about something called the gradient ascent method. Okay, so it's the opposite of the gradient descent. Okay, fine. So, and of course, if you trained a machine learning model or let's say deep learning model before, I'm sure that and you did you let's say you worked with optimizers. I'm sure that you had faced something called the learning rate. Okay, so the learning rate is a tuning parameter also, is let's say a tuning parameter in an optimization algorithm that determines the step size at each iteration while moving toward the minimum loss. Okay, so as we all know in our models, so the more our loss is lower, the more our model is better or good. Okay, so in all this work, what we are working, the main thing that we're gonna do is to have the minimum loss function here. Okay, and this learning rate help us. Okay, so the learning rate can be set algorithm designer or let's say the developer who build our model. Okay, so the engineer or the developer set the number of or the size of the learning rate, the number of steps. If we use a learning rate that is too small, it will cause, let's say, x to update very slowly. Okay, so here we have this x-axis. So if we have a learning rate, let's say a too small learning rate, this x here will update very slowly. Let's say requiring more iteration to get here to the lowest loss function or the best solution, because as we know the lowest loss function is the best solution and the solution that we want to reach. Okay, so here we will have let's say we'll have more iterations. Okay, so with a small step or small learning rate, here we will have a small iteration and we will move slowly to reach here the bottom or the lowest loss function. Okay, and conversely, if we can let's say if we use a higher learning rate, so it must more larger. Okay, so here we have those two graphs here with a small learning rate, so we're moving step by step to reach the bottom here, and in the other side we have the second graph with a larger learning rate, so here we are jumping in a large way, and this graph here represent the gradient descent. Okay, so to let's say to find the minimum loss, let's say the lowest loss function here, we will use let's say a small learning rate. Okay, so moving now to the second example or the second type, which is the stochastic gradient descent. Okay, so here the word stochastic means a system or a process that is linked to a random possibility. Okay, so here while talking about stochastic gradient descent, so here we're talking about some randomness, some random possibilities. Okay, so it's a variant a little bit of a gradient descent. It tries to update the model's parameters more frequently. I mean, more than the normal gradient descent. In this model, parameters are altered after computation of a loss on each training example. So if the data set contain, let's say 1,000 rows, this stochastic gradient descent will update the model parameters 1,000 times, okay, in one cycle of this data set. Okay, so here we use in the gradient descent, we use to update those data once after moving or after checking all the data sets. Let's say yes, we update parameters after checking all the data sets. So here the with the stochastic gradient descent we'll be able to change those parameter, let's say the number of data. If we had let's say 1 million data, so the parameters will be updated 1 million times in cycles of this data set. Okay, so stochastic gradient descent comes to reduce stochastic in a plain terms, I mean randomness. So this SGD or a few samples are selected randomly instead of this whole data set. Okay, so in the opposite of only gradient descent, the stochastic gradient descent select only some, let's say, select randomly this instance from data set for each iteration. In gradient descent, there is a term called batch, so which denotes the total number of sample from the data set that is used to calculating the gradient descent for each iteration. In typical gradient descent optimization, like let's say a batch gradient descent, the batch is taken to be the whole data set. Okay, so although using the whole data set is really useful for getting the minimum in a less noisy and less random manner, but the problem arises when our data gets bigger. Okay, so just like imagine, suppose we are having 1 million samples in your data set. Okay, so here, if you use a typical gradient descent optimization technique, you will have to use all this 1 million samples. Okay, you will have to use all those 1 million sample for completing one iteration while performing the gradient descent, and it has to be done for every iteration, okay, until the minimum is reached. Okay, so if we have, let's say, 500 iterations, so all this 1 million data set will be reached, let's say, we'll take the time of all those 500 iteration. Okay, so it became computationally very expensive to perform. Okay, so the problem to solve by stochastic gradient descent is in stochastic gradient descent, it's used only a single sample, let's say the batch size of one. Okay, so instead of batch size of the whole data set, here in stochastic gradient descent, we will take a batch size of one to perform each iteration. The sample is random shuffled and selected for performing iterations. Okay, so here is a graph showing the difference between a normal gradient descent and stochastic gradient descent. Okay, so in stochastic gradient descent, we found out the gradient of the cost function of a single example at each iteration, instead of the sum of the gradient of the cost function of all the examples. Okay, so in SGD here, since only one sample from the dataset is chosen at a random for each iteration in the path taken by the algorithm to reach, let's say, the minimum, which is here. So it's usually noiser, this graph shown here, it's noiser to reach the minimum, comparing to, let's say, the typical gradient descent algorithm, which is, let's say, a straight path to reach the minimum. Okay, but that doesn't matter all that much, because the path taken by this algorithm does not matter. Okay, so as long as we reach this minimum here, so with significant shorter training time. Okay, so here is the main, let's say, the main difference between those two algorithms. So here, just because we are taking those samples, we are taking our data randomly, so we have this noise here. That's what you call it, noise, by going up and down more and more till which we reach this here, this local minimum, or this local let's say here this minimum loss function. Meanwhile, in gradient descent, while iterating the whole data set, so here we have this straight path. Okay, so yes, this is the one thing that have to be noted here, is that stochastic gradient descent is generally noisier than the typical gradient descent, and it usually took a higher number of iteration to reach that minimum. Because of it, randomness in the descent. Okay, so even though it's require a higher number of iteration to reach that minimum, then typical gradient descent is still computationally much less expensive than this typical gradient descent. Okay, so in most scenarios, stochastic gradient descent is preferred over a batch gradient descent. Okay, so this, we call it a batch gradient descent for optimizing a learning rate. Okay, as long as the path of our let's say the path of our performance, or the path to reach is this minimum loss, is let's say we don't take it, it doesn't matter, we don't take it in consideration, so we don't care about this noisy path here. Okay, as long as we reach the minimum loss function. And of course, there will be much number of iterations comparing to the typical one, but even though the stochastic gradient descent better than this typical gradient descent. Okay, I hope it's clear so far. Now, as I said, that's what we call it, the batch gradient descent, because we take, let's say, a batch size, the whole data set, or the whole number of sample is the whole data set. Okay, so we call it a batch gradient descent, and this is stochastic gradient descent. Now we will see another example, or another type, if you can say. So depending on the number of training example considered in updating the model parameters, let's say we have 3 types of gradient descent. Okay, so here we're still talking about gradient descent. Okay, so the basic or the root thing that we are talking about here is the gradient descent, and we change the number of samples or a number of training example taken in consideration while training our model. Okay, so as I said, we have, let's say, 3 types of gradient descent. We have the batch gradient descent. Parameters are updated after computing the gradient error with respect the entire data set, or the entire training set. And we have stochastic gradient descent, where parameters are updated after computing the gradient of error with respect to a single training set example. Okay, so in the batch gradient descent, we take the entire data set. Stochastic gradient descent, we take a sample by sample. Okay, so we take in consideration a single training example. And here with the mini batch stochastic gradient descent, parameters are updated after computing the gradient error with respect the subset of the training set. Okay, so let's say we divide our data set, we divide our example to some batches, and here to use this batch stochastic gradient descent. Okay, since it's a subset of training example, is considered, it can make, let's say, it can make a quick update, because as we said, in stochastic gradient descent, there is a number, let's say, there is a huge number of iteration which occur, it takes some time to reach this minimum of loss function. So here, while using this the subset of training example here in batch stochastic gradient descent, so here it's make a quick update in this model parameters, and can also exploit the speed associated with the vectorizing the code. Okay, so here the mini batch gradient descents may make a compromise between a speedy convergence and the noise associated with the gradient update, with makes let's say, which makes it more flexible and robust algorithm. Okay, So here is, let's say, a small comparison between those two algorithms. So depending upon on the batch size, the update can be made less noisily, as you can see here in this in this graph here. So here, let's say those are the updated, and they are less noisily, greater than the batch size less noisily here to update the information to get to update the parameter, sorry, to get here to this the lowest loss function. Okay, and let's say the mini batch gradient descent attempt to find the balance between the robustness and that, let's say, the stochastic gradient descent and the efficiency of batch gradient. Okay, so it's the most effective implementation of gradient descent, which is used in the field of deep learning. Okay, so far this is the most efficient one because we have less noise, less iterations comparing to this one. Okay, so we are okay. We agree that the stochastic gradient descent is much better than gradient descent, even that we have much iteration. We have, let's say, this noise. And here with those mini batch gradient descent, it's much better than this stochastic gradient descent. Why? Because we reduce the time taken, we reduce the number of noise here, okay, and also we reduce it a number of iteration to reach here the minimum loss function. So here, okay. Now let's talk little bit about this term, which is momentum. Okay, so we reviewed what happened when performing stochastic gradient descent, when performing the optimization where only a noisy variant of gradient is available. Okay, so in particular, we notice that for noisy gradients, we need to be extra caution when it comes to choosing the learning rates. Okay, so here to choose a learning rate in face of those noise, of course. So if we decrease, let's say, if we decrease the learning rate too rapidly, it will converge, of course. And if we are too long, we fail to converge to a good enough solution, since noise let's say, keep on driving us away from this optimality. Okay, and here we are facing the two main problems, which are the leak averages and an all condition problem. Okay, so here came this momentum was invented for reducing a high variance in stochastic gradient descent and soften the convergence. Okay, so it accelerates the convergence toward toward, let's say, to needed, or let's say to the relevant direction, and reduce the fluctuation to the irrelevant direction. Okay, so yeah, that's it. So one more hyperparameter is used in this method, okay, known as the momentum symbols by this y here. Okay, and we have this function written here to determine and to include this symbol of momentum. And now the weights are updated using that form here. And the momentum term is usually set to 0.9 or a similar value. Okay, so generally it's 0.9. So yeah, that's in general about gradient descent and including momentum. Okay, I just like to move to a Jamboard to explain better, let's say, this idea. Okay, so we have this data set in the first type. We have that, let's say, this data set of, let's say, 1,000 samples. Okay, so by using the simple or the typical gradient descent, we will have this graph here. Okay, so of course, our objective is to reach the minimum loss function here, which is here. Here is the minimum loss function. So here, our model will try to adjust weights and, let's say, biases to reach this minimum learning rate. Okay, but here in this gradient descent, so here we are talking about the typical gradient descent. Okay, so as I said, the weights is updated once after seeing the entire data set. Okay, so if we set the number of iteration to 50, okay, so this is the number of iteration. So the gradient descent or the weights of this gradient descent will be updated once after seeing, let's say, the whole data set. Okay, so in general, we have 50, 50 updates or 50 changes, because after each we all agree that number of iteration. Okay, so we call an iteration when seeing or when passing through all the entire data set. Okay, so after passing through the entire data set, we change parameter. So that's why we have, let's say, this large jumps. So here, moving from this point here to this point here, moving from this point here to this point here, etc. Okay, so here theta can make only large jumps. Okay, so here we are talking about weights. I'm sorry. So and of course we have some few step of iterations. And the solution here was to use, let's say, to update parameters frequently. Okay, so we don't wait until the whole iteration to end to change our parameters or to update our weights. So here they propose to update the parameters frequently. Okay, so we don't wait until all the whole data set being passed or proceed by our model. And here came the solution of stochastic gradient descent. Okay, stochastic gradient descent. Okay, so here we have our graph. Fine. So what's the main role of stochastic gradient descent? He makes sure that our samples are randomly he pick those samples randomly. Okay, so let's say and he change and update the parameters, and let's say update after these parameters after seeing each data point. Okay, so let's take this first example here. Here we update, he will update the weight. Okay, so let's say our model, let's say, I'm sorry, sorry. Okay, where am I? So as I said, okay, I'm sorry. So he take a sample by sample. Okay, so let's imagine we are dealing here with the classification model to set whether this image, let's take these samples here are images as images, so to check whether this image is a dog or not. Okay, so here the first thing, he will check if this is a dog. So yeah, it's a dog. He will let's say step by one. And then the second image, also it's a dog. I mean, is typical or it's similar to the previous one. So yeah, he will make another step right here, and boom, this one is a cat. So he may come back again. So that's why we have those noise. Okay, if you remember, in the graph we had that noise to reach our minimum loss function here. Okay, so that's why, because he's updating parameters after seeing each data point. Okay, so those that's why it's make noisy jumps. Okay, so he go forward and then go backward and so on. Okay, so because here there's noise until we reach, as I said, he will go with the small steps until we reach here the minimum. Okay, but it's not only in a forward direction. I mean, here in when there is not a similar picture to the previous one, he may go back. But what we are sure about it is that he will reach the minimum point in a perfect way. Okay, so here in general, stochastic gradient descent is influenced by each sample here. Okay, but that wasn't good enough because we have too much noise, we have too much iteration. Okay, so here number of iteration will be number of each sample here multiplied by the number of the whole iterations. Okay, so here we have, let's say, an extra numbers of iteration. So that's the solution is to use the mini batch stochastic gradient descent. Okay, so we just with the same idea behind stochastic gradient descent, we will move to the mini. Let me write it. Okay, the mini batch gradient descent. So here is our graph. The weights here are updating after seeing few samples. Okay, so let's say, for example, this is the first batch, this is the second batch. Okay, so he won't change here after each sample. Okay, so after seeing a couple of samples here, he will iterate through our graph here to reach this minimum or this loss function. Okay, so this is the idea in general. This mini batch here, we reduce the number of iteration because as I said, we have the number of samples multiplied by the number of iterations, so here represent the number of iteration. Meanwhile, the mini batch will be a number of batches here multiplied by the number of iteration, which is, let's say, less noisy, and we have less number of iterations. Okay. And of course, there is that term of memento, as I said, where the model, it's another way to let's say, to decrease the noise, where our model can learn faster and paying a little attention to the few examples here, just like this term or this notion of graphs. And let's say it's throw it off from time to time. Okay, so it's also a better solution to add new hyperparameters called, let's say, momentum. Okay. So let's carry on with the other examples or the other common or most used optimizers. Okay, fine. So we have this ADA grade. One of the disadvantages of all the optimizers explained before is that the learning rate is constant for all parameters. Okay, just to clarify something, the learning rate is the number of steps. Okay, or the step size to iterate through our graph, if you can say. Okay, so one bad point is that one bad point about all the previous algorithm or all previous optimizers seen before is that they have a fixed learning rate or a learning rate which is constant for all parameters and for each cycles. Okay, these optimizers change the learning rate. So this ADA grade change the learning rate. It changes for each parameter and at every time step t, let's say. Okay, so it's a type second order optimization algorithm. It works on a derivation of an error function. Okay, so here let's check together the advantages. Okay, so we have the learning rate change for each training parameter. And we don't need to manually tune the learning rate and able to train, let's say we are able to train on sparse data. And one of the bad points or one of the disadvantages is that computationally expensive as a need to calculate the second order derivation, and the learning rate is always decreasing, result in slow training. Okay, so this is about the ADA grade. We have, let's say, another example or another optimizer, which called the root mean square propagation, or as we call it, or as we use it typically, the S propagation. Okay, so this optimizers, let's say this optimizer has an intensity history. Let me tell you first about the history behind this optimizer. Okay, it was first devised by legendary with called Hinton, I think. Yeah, while suggesting a random idea during his Coursera class. Okay, so he invented or he discovered this new optimizer or this root mean square propagation while giving or while suggesting idea about Coursera class. Okay, so this RMS propagation also tries to dampen the, let's say, the oscillations, but in a different way than the momentum did before. So here the RMS propagation takes away the need to adjust learning rates. Okay, so in the previous optimizer, we was adjusting our learning rate after each iteration. Okay, so here it's take away the need to adjust those learning rates and does it automatically. Okay, so more so have this optimizer choose a different learning rate for each parameters. Okay, in each time we change or we update our parameters, this optimizers change automatically this learning rate. Okay, so the method in which the learning rate is adapted for each of the parameters. The idea is to divide the learning rate for weights by running averages of the, let's say, the magnitude of the recent gradient for the weight. So first, the running average is calculated in term of mean square of the mean square, yeah. And yeah, we have it has shown a good adaptation of learning rate in a different application, if I can say, and can be seen as a generalization of the root propagation. Yeah, because it's, let's say, involved or inspired from this optimizer, and it's capable or able to work with the mean batch as well, opposed in the only to all the, let's say, the entire batch, or as we call it, the full batch. Yeah. Okay, so this is about the root mean square propagation. And last but not the least, we have this ADAM, or the adaptive moment estimation. Works also with it works also with momentums. Okay, so as a first and the second order. Okay, so here we go to the second order. So the intuition behind the Adam is that we don't want to rule so fast just because we can jump over the minimum. Okay, we want to decrease the velocity a little bit for careful research. Okay, so in addition to storing an exponentially decaying average, the past square gradient, like ADA delta or the ADA. Okay, so it's also help exponentially decaying the average of the past gradient. Let's call it MT. Okay, so this MT and VT are values of first moment, which is the mean. Okay, so it's simply the mean, and the second moment, which is the uncertain variance of the gradient respectively. Okay, fine. So we are taking the mean of the MT and VT, and the ET of MT can be equal, where this ET is an expanded values of our function, which is fx. Okay, so here let's say we have moments update for every parameters, and this is what make this Adam optimizer special. Okay, so here we're changing, we don't have a fixed learning rate, and also we have this momentum updated for every parameters. Okay, so here as we are building this momentums over time. Okay, and at the same time we are updating those learning rates. Okay, so to check the sorry to know about the advantages or the of the Adam and the disadvantages. Okay, so we have the method is too fast and converge rapidly, and rectifies vanishing learning rate and the high variance, and also, as I said, building the momentum over the time. And one of the disadvantages is that computationally costly. Okay, so yeah, it's cost too much. but it stays Adams. We can choose it as the best or the perfect optimizers, and it's the most common use optimizer ever. Okay, to sum up or to conclude, let's say Adam is the best optimizer. If one wants to train a neural network in less time and more efficiently, then Adam is the optimizer. Let's say Adam use momentum and adaptive learning rate to converge faster. And for sparse data, use the optimizers with dynamic learning rate. Okay, so we're talking about dynamic learning rate because they are updating over time. They are updating after each parameter. Okay, so and one last point: if we want to use gradient descent algorithm, then the mean batch gradient descent is the best option. As we saw, we have less iteration and we have less noise. Okay, but yeah, of course, we can select Adam as the best optimizer. Okay, and you may ask a question how to use or how to know which optimizer I should use. That depends on your case and that depends on your problem you're trying to solve. Okay, so each optimizer have his advantages and disadvantages. So based on the number of your data set, number of samples, the type of your problem, let's say if it is a classification or regression and so on. So based on those information, you can choose which parameter or which optimizer suits your solution or suit you well. Okay, so by that we reach the end of our session. If you have any question, don't hesitate to ask. We'll have like 5 minutes to answer your questions. Please, if you have any question, don't hesitate to ask. So fine, it seems like you don't have any question. Thank you so much for being here and see you in next session. Thank you so much. Bye bye.